We've seen how to break a vector up into components. We've seen how to represent that vector in terms of unit vectors, in terms of x and y components, or in terms of a magnitude and direction. We've seen how to represent three-dimensional vectors, and we've seen how to rotate our axes and find new components relative to new axes. All of these have been ways of finding vector components. What we're going to see now is why we care so much about vector components, why they are going to make life so much easier for us when we start using these in practice. We've seen how to do the graphic method of vector addition. If I have a vector A and a vector B, I can use the tip to tail method and find vector C, where vector C starts where vector A starts, vector C ends where vector B ends, and so vector C here is A plus B. We can add them using the tip to tail method or using the parallelogram method, but we've seen how tedious that is to use a ruler and a protractor, which still isn't the most accurate way possible. If we are just freehanding, then it's going to be even less exact, and so we want to find another way to be able to use our calculator and find calculate these vectors more precisely. And so what we can do is look at this. We can look at this vector C here, and we can see that this would be Cx. This is the x component of vector C, right? If we take this full vector and project it onto the x-axis, this would be Cx. And we would see that this here would be Cy. Again, we're taking this full vector and projecting it onto the y-axis. This would be Cy. And we could do the same thing. A would have components Ax and Ay we've seen, and B would have components Bx and By that we've seen as well. And so what we notice here is that Cx is Ax plus Bx, and Cy is Ay plus By. Because if we can break up C into Cx and Cy, and we can break up A and B into vector components as well, then we said that the x components are all going to be parallel or anti-parallel to each other, so this plus this gives us that, and then the y components are all parallel or anti-parallel to each other, so those are going to add as well. And so when we're trying to add or subtract vectors, all we have to do is break all the vectors up into components. We break all the vectors up into components, and then we just add them all up, and the component of the resultant vector is just the sum of all of the corresponding components of the input vectors. That's true in the x direction, it's true in the y direction, and then the x and the y direction are perpendicular to each other, so they are orthogonal. That means they have no crossover between each other. They basically don't see or affect one another. So the real key to using components is that you can break vectors up into components, and you can do all of the normal mathematics that you typically do all in the x direction to get to find the effect on the x component. You do all the math that you know how to do in the y direction to get the y component, and then you can put the components back together as a magnitude and a direction if you need to. But breaking things up into components gives you a bunch of parallel and anti-parallel vectors for which the normal rules of mathematics work. So for example, let's assume that we have vector D, where D is the sum of vectors A, B, and C. So we're going to assume D has two components, dx and dy. This is the x and y components of D. We know that this is the x component because it is paired with the I hat vector that points in the x direction. We know this is the y component because it's paired with the j hat vector that points in the y direction. And we can assume that the A, B, and C all have x and y components, assuming these are all two-dimensional variables. And so these are all numerical quantities. These would just be numbers. And then the I hat and the j hat are giving us the direction, either showing that this points along the x-axis or this points along the y-axis. And so if we're adding these numbers, we can only group them so that all of the I hat vectors go together, for example. The same way in algebra, if you have 2x plus 3y plus x plus 2y, you can add the x terms and you can add the y terms, but the x's and the y's all stay independent of one another. You can't combine them. The same thing is true here. You're going to have, these are all going to be numbers, but you can add the I hat terms and you can add the j hat terms, but you can't add I hats and j hats because they're pointing in different directions. They don't deal with each other. So all of the x components can all be grouped together. When you add all these up, they have a common I hat that we can factor out. And we can do the same thing with the j hats that are all pointing in the y direction. We have a common j hat when we group those together that we can factor out. And so in this case, basically, if we have an I hat here and an I hat there, we know that's the same. And so then this part and this part have to be the same. And we can say that the x component of our resultant vector is just the sum of the components of the inputs. We can do the same thing here. The j hats and the j hats match, so whatever we have here has to match whatever we have there, and the y component of the resultant is the sum of the y components of the input vectors. So again, with a little bit of investment at the beginning, we have to break all these vectors up into components, but then it's just straight math. We just add the components, and we get the components of the resultant, and we know precisely the values for the resultant vector that we have without having to try to add these vectors using angles, using laws of sines or laws of cosines, or any of those other more difficult concepts. It's just straight summation here. If we are subtracting two vectors, exact same thing before, right? We're going to imagine each one of these vectors has x and y components, and we'll group the x components together with the I hats. We'll group the y components together with the j hats, and then at the end of the day, the x and y components of the resultant are the difference of the x and y components, respectively, of the input vectors. If we are multiplying by a scalar, so here we have vector t is some scalar, some number, c, times vector s, then this vector c, or this scalar c, multiplying vector s here, which we have broken up into its components, basically this scalar is just going to distribute into that vector, and it will show up in both of our terms. And thus, the x component of t is the scalar times the x component of s. The y component of t is the scalar times the y component of s. If we are multiplying the vector by a scalar, we're just multiplying all of the components by that same scalar because we're distributing the scalar into the components. Again, we're just assuming c is some scalar. We haven't said whether it's bigger than 1, less than 1, whether it's negative or positive. That doesn't matter. You just do the math, and it tells you what the components of your other vector are, of what your product is of that scalar and vector. And so all the multiplication and division that we would do, we can just distribute. We can just do component by component. All the addition and subtraction we can do component by component. So in practice, what we'll do is use the tip-to-tail method to sketch out the sum of the vectors to get an idea of what the resultant should look like. Then we break all those vectors up into components, and then we can add all the components together to find the components of the resultant, and then we can put the components back together and see whether the resultant vector looks like we think it should have looked like based on our initial sketch. Again, our method is to use the tip-to-tail method to sketch the vectors to get an estimate of what the resultant should look like, or to find the quantity that we want to find. Then we'll decompose all the input vectors into their components. We can add, subtract, or otherwise combine the corresponding components. All the x components go together, all the y components go together. X and y components don't see one another. They are independent of one another. We use those input components to find the components of the resultant vector. And then once we know the components of the resultant vector, we can find the magnitude and direction. We can compare what these values look like to the answer in step 1. The components that we find for the resultant vector are mathematically much more precise, but the sketch is a good way to confirm that we've done the math correctly and that our answer makes sense.